Right. Very good morning to everyone. Good morning or good afternoon, wherever you are. So it's my pleasure to invite Dr. Ifana Mahbub. Uh, she has been a good friend, and more than that, she has been she has been an extremely successful professor. She is currently with University of Texas at Dallas as an assistant professor, and she is also Texas Instruments Early Career Award winner. She has numerous awards to her credit, including NSF's Career Award, Young Investigator Awards from Department of Defense, and many others. So without much discussion on introduction, I would like to invite uh, Professor Ifana Mahbub to give her presentation on beamforming and beam tracking system for vehicle-to-vehicle wireless communications.
Thank you, Kamesh, for the nice introduction, and good morning, everyone. Welcome to the presentation. As Kamesh mentioned, today I'm going to talk about the beam steering and beam tracking system for vehicle-to-vehicle wireless communication. So as you all know, wireless communication for vehicle vehicle directions and to avoid collisions, it's highly important to have interconnected and reliable wireless communication. As you can see, the next era of modernization of city would require all sorts of communication between different links, buildings, autonomous vehicles on the road, as well as autonomous vehicles on the air. And of course, for this reliable communication, we need also some sort of steering mechanism, because these are mobile vehicles, as well as we also need high data rate communication and all sorts of privacy and security. If we look into some of the challenges that we have in the V2V communication area, the first and foremost is the interference, because depending on the band the communication is happening, interference is very much prominent. And then on top of that, the signal attenuation is a big issue, because if depending on the frequency as well as the environmental scenario, the signal can be highly attenuated. And to compensate for that, it is of utmost importance that we have a very high gain and directive communications and antennas integrated in the system. And the mobility and dynamic topology is another concern, because these UAVs or autonomous vehicles on the road, they are mobile and moving at a high speed. So we have to also take into account that to establish a reliable communication system between these vehicles, we have to also incorporate high speed beam steering. And then depending on the band, sometimes we want to operate at a higher frequency to avoid the limited bandwidth issues, because for UAVs, for example, it might be required that we need videos to be captured and then transmitted wirelessly, which requires high data rate. As I mentioned, security and privacy is always a concern, and more importantly, energy consumption or the system needs to be lightweight, right? Because if it is heavyweight as well as it requires a lot of power, then it would need heavy batteries to be carried by the UAVs, and that would increase the payload. And then various regulatory and spectrum allocation issues are there, and then weather conditions, as I mentioned earlier, and then line of sight communication and non-line of sight communication is always a challenge. So with that, let me show you a case scenario where different losses and problems and challenges that occur in a typical communication system that is established for drone to drone or vehicle to vehicle, specifically UAVs. That's what I have been targeting for this talk. So typically, a ground-based station would be connected with the UAV for navigating, and over there also some sort of beam steering and beam alignment is needed. And if there is some sort of beam misalignment, meaning there is a difference between angle of arrival and angle of departures, then there is always loss of information. And then on top of that, there is atmospheric attenuation that plays a role, and I'll talk more about it in the later slides. Specifically, when we are talking about really high frequency, specifically millimeter wave frequency, the wavelength is almost the size of the raindrop that are, if rain happens at that time. Then that causes the scattering and absorption, which can cause problem in the, increase the path loss basically, and the propagation loss. Then when from UAV to UAV, there are a couple of things that also are important to be considered. The first thing is the element that we place in between an active circuit. For example, in this case, the active circuit could be the beam steering chip, which has the phase shifters, voltage control oscillators, power amplifiers, so on and so forth. And then there is a transmitting array antenna. In between these two components, there is the feeding loss due to the mismatch of impedances and the insertion loss of the power dividers that we typically use to branch out the different arrays. And then on top of that, the typical loss between a transmitting and receiving antenna is the propagation loss. And as we are gonna increase the frequency to increase the data rate to reduce the interference, there is always the challenge of the huge propagation loss that we are going to observe because of the wavelength being much smaller. And then on the other side, there might be multiple UAVs. So there is always the need to track and do beam steering. Otherwise, if the beams are highly directive and they are not aligned properly, the loss of packets and information is prominent. So with these challenges in mind, I, along with my colleagues, started this project, and this was funded by NSF. The project is titled Rings Mobility-Driven Spectrum Agile Resilient Millimeter Wave Communication Links for Unmanned Aerial Vehicle Traffic Management in the Sky. The PI of this project is Dr. Kameshna Muduri, and along with me, the co-PI is Dr. Xiang from University of New Mexico. So the idea that we have for this project is that much like the roads and highways for the cars that we have, in the future we'll have similar need for roads and highways in the sky for unmanned aerial vehicles. And in the sky we cannot have, lights to stop and, monitor the traffic. So obviously that traffic lights need to be replaced by robust communication systems so that the collisions can be avoided. Like, for example, in this figure, you can see the depiction of this highway that is planned to be implemented. And I think Dr. Namudari is working with various collaborators in NASA and all that, how to actually realize this, very futuristic vision, and how to implement these various eastbound, westbound, southbound, and northbound highways for UAVs. And they can transition, the UAVs can transition from one level to another level. So all this sort of, highway in the air requires the communication and short link distance communication mostly between the UAVs. And it might be possible that there is some sort of, the storm that's coming, and then the UAVs in the front need to make aware the UAVs in the back that are following to make sure they're going to slow down and, change route as needed. So in my group, what we are particularly doing is building the hardware prototype, basically the antennas and the interface for this sort of communication. So we're in the physical layer, even down like in the hardware domain that we are investigating. And this research, we have mainly two research questions that we posed. One is how to efficiently design the phasor antenna to achieve maximum gain, bandwidth, steering angle, and minimum beam width. So these gain basically would enhance reduce the path loss. Bandwidth is needed to be increased because we need high data rate communication. By achieving a wide steering angle, we can increase the coverage area. So we can, imagine we would probably need 360-degree coverage. While a specific array antenna cannot achieve 360-degree coverage, we can place the arrays of antennas in strategic ways on the UAV to basically achieve close to 360-degree coverage. And also the minimum beam width would mean more gain and lower side lobe levels. That means radiation in the undesired direction will be minimized. The second question that we are investigating is how to implement an efficient control algorithms to automatically track and steer the beam through electrical beamforming and mechanical steering. We're mostly looking into electrical beamforming, but mechanical steering could be possible because sometimes, the UAV wings could be rotated and we can integrate antennas on the wings so that we can do mechanical steering. But that would require an additional, motors and control algorithm. So the particular band that we are looking at is the millimeter wave band. What is millimeter? Millimeter wave frequency refers to the range of electromagnetic waves with wavelength in the range of 1 to 10 millimeter, which corresponds to 30 to 300 gigahertz. And again, this is a very wide frequency range, and there are particularly various bands within the 30 to 300 gigahertz. 300 gigahertz, some people like to call it sub-terahertz region. And as I mentioned, there are V band, W band, all sorts of band in between. For our particular work, we have been mostly investigating in the V and W band. So 40 to 75 gigahertz is the V band, and 75 to 110 gigahertz is the W band. You might be wondering, why did we choose this specific frequency band? The reasons are obvious because the antenna size could be much smaller as we increase the frequency. And as a result, we can reduce the aperture size while also achieving similar or higher gain as opposed to working at lower frequency. That would reduce the payload. And we can obviously see these bands are not like as highly utilized as the other bands like, S or C band. So for that reason, we can reduce the interference and congestions and all sorts of latency issues. And then although the problem is the attenuation, as I mentioned earlier, but we can have higher gain antenna arrays without increasing the aperture size, which can compensate for the attenuation. And obviously the other benefit is the throughput could be much higher. So I was talking about some of the problems that we have. As you can see, the attenuation could be much higher, and specifically at certain frequencies. For example, here you can see this is an example of attenuation, which is dB per kilometer versus frequency. And at different frequencies like 60 gigahertz, the attenuation is much higher. And in the same case at 120 gigahertz or 180 gigahertz, there are particular frequencies where attenuation is specifically really high. So as you can see, when the wavelength is large compared to the size of the raindrops, scattering is predominant. But when the wavelength is small compared to raindrop size, attenuation due to absorption is predominant. So we need to take into account all this case scenarios or specific frequencies where the attenuation is stronger, and then work around with it. And that's why our proposed systems are mostly wideband type of systems, which can allow to make the operation happen at different frequencies as well. And then some sort of security systems can be enabled to do frequency hopping if needed, so that eavesdropper cannot do jamming of the system. So here I have highlighted various pros and cons of millimeter wave. As you can see in this very figure, a 3 gigahertz system or antenna, the aperture size and a 30 gigahertz aperture size, if we assume the aperture sizes are same, then we can see a 30 gigahertz antenna can achieve a higher distance and similar gain as opposed to 3 gigahertz. So that's basically the in a nutshell, we can say that we can compensate for the path loss by scaling up the arrays, even though it won't take too much space on the UAV as opposed to a 3 gigahertz system. So that's why we have been motivated to move to the UAVs. And the other things that I mentioned, the higher data rates and wider bandwidth is possible in the millimeter wave frequency. And some of the cons that I already talked about is higher atmospheric attenuation. As you saw in the previous graph and here as well, there are various water molecules in the atmosphere that can increase the attenuation specifically for specific frequencies like 60 gigahertz, as you can see here. The other challenge with millimeter wave frequencies is the complexity in the feeding network and the insertion losses of the system. And it gets much more challenging when we need to scale up the system as we're going to have number of elements increased, then the beam steering algorithm and the whole system gets much more complicated. And then the external noise can also cause interference. So obviously, to compensate for the high propagation loss at the millimeter wave frequency, it is obviously needed that we need to achieve very high gain. And typically in the antenna domain, high gain is achieved by creating an arrays of antennas, something like this. So an array could be a linear array or circular array or this form of rectangular or square-shaped arrays. Those arrays, what it does basically is that as we are going to increase the number of elements, it increases the main lobe gain, albeit there are some side lobes that also gets created. Moreover, these highly directed pencil beams can be radiated or directed at various directions by implementing a scheme called beam steering. And I'm going to talk more about that. But you might be wondering, is there any bottleneck of this system? Obviously, there is bottleneck. We cannot scale up the array and increase the gain linearly as we would like, because as this number of elements are going to increase, what happens is that the side lobe levels gets higher and higher because this whole arrays create a combined array, and as we're going to do beam steering, this side lobe levels gets more prominent, and the higher the side lobe level, the lesser the main lobe gain, and as a result, we see that the peak gain is dropped more than 3 dB or 50%, which basically means the 50% or more power is being lost for the radiation at undesired direction. And as a result, we cannot make it operate for a wider scanning range. So that's basically the bottleneck that we need. I mean, it's a challenge in terms of beam steering. So here's an idea about the electrical beam steering. So in the simple terms, what happens in electrical steering is that the elements in the array are provided a specific phase shift between the elements. As you can see, for example, the first element has a theta, which is the, let's say, the phase of the signal that is being fed. And then an additional 5 phases added to the second element, and then 2 phi, 3 phi, 4 phi, so on and so forth. And this phi basically causes the overall pattern to be steered at various desired directions. And if there is no phase, like phi equals to 0 degree, we expect the beam to be in the bore side, which is a theta equals to 90 degree angle. So, and this is basically for planar array. So we assume the arrays are in a plane fashion. And then beam steering can also be implemented using amplitudes, and this is also known as, amplitude Gaussian type of patterning that can also achieve beam steering along with the phase shifting. But anyways, so if we look into the equation for the signal to be fed to the antenna array, this is how the waveform equation looks like. And this is basically the different amplitudes for the n number of elements, and the corresponding phase represented as this. So the phase shift, the maximum allowed phase shift d phi, is defined as k ls root over epsilon r, where k is the wave number, 2 pi by lambda, ls is the distance from the wavefront, and then the epsilon is the dielectric constant or permittivity of the substrate, relative permittivity. So typically in a beam steering system, the spacing between the elements are kept to be less than lambda by 2, where lambda is the wavelength, which is defined as the velocity of light in the vacuum, which is c, which we all know, 3 into 10 to the power 8 meter per second, and divided by the frequency of operation. So although it's like traditionally it's lambda by 2, but sometimes specifically for lower frequency, and since the wavelength is much smaller, it might cause overlap of between the elements. So sometimes it could be possible that more than lambda by 2 spacing is implemented to optimize the beam pattern. So there are various means of beam steering. I'm just going to talk briefly about those various ways. The first one is analog beam steering, where basically analog components are used in the system. So you can see there is the RF chain, which probably includes the VCO and the mixer. And then for phase shifting or provide the various phase shifting angles for various elements in the array, an analog phase shifter is used. So this approach is cheaper, and compared to other approaches, it might be low power if we can design the phase shifters in a low power fashion or reduce the insertion loss. But this is hard to make it wideband, because if, for example, we want to cover the whole V band, which is 40 to 70 gigahertz, it would be really hard to design these wideband elements, especially the phase shifter, to give the same phase degrees for various frequencies. And also the system could be very large and inefficient in a way that if you have like very high number of elements in the system, let's say hundreds of elements, then you would need individual 100 phase shifters, which would basically increase the cost and increase the complexity in the operation. And then there are various sort of phase shifting elements that are needed, right? Like the varactor diode or some sort of FET-based or field effect transistor-based phase shifter designs need to be incorporated. And controlling this phase shifters, for example, if it's a voltage control, varactor that has 3-bit quantization. So each of these will need 3-bit control system, which would increase the complexity of the system. On the other hand, the digital beamforming system is much better in that sense. It can it basically controls the delay, because delay is corresponds to phase, and by controlling the delay, we can do the phase shifting. So this whole operation is done using beamforming algorithm implemented on the digital domain, and then that drives the RF chain to drive the antennas in the array. Again, frequency of operation needs to be higher, because we know in digital domain, the frequency corresponds to the frequency. And then the ADCs and DACs are needed, and that also consume a lot of power. The hybrid is the sweet spot between the analog and digital. So basically there is beamforming algorithms implemented on the digital domain, and then there's RF chain, and then there's some analog phase shifters implemented. And that could be optimized to achieve low loss. And as I talked briefly about the mechanical steering, which we probably have seen in weather radar applications where the array are physically rotated to achieve various beam steering, and Doppler weather radar typically of that type of antennas or arrays. And Vivaldi antennas could be one example where you can have highly directive pattern, and then we can do mechanical steering of that. And we have been working with Vivaldi antennas for mechanical steering. So quickly, I'll just give some brief background about tracking techniques. So why do we need tracking? We need tracking for target detection. We want to know what's the range of the target from the source, and finding the specific azimuth and elevation angle of that, and finding Doppler frequency shift. So this could be the information that's needed for tracking. So angular tracking, which consists of, which can be divided into two parts. One is the sequential lobing and one is the conical scanning. So what happens in sequential lobing is basically there are two beams that are sent, but in time intervals. For example, first beam A is switched on and then beam B is switched on. And each beam, as you can see in the dashed line, has a beam axis. And typically when the object that we're trying to identify is on the beam axis, then the beam pattern gets high output return. Basically, there is a scattered signal that would come back in the same beam, and we would have higher amplitude. So for this first example, as you can see, when we have the object that is not on the beam axis of these two lobes, then the return signals or return voltages are of same amplitude. But when the object is on one of the beam axes, then we can see a higher amplitude on the axis that this target is located. And from there, we can track the position of the object that we're trying to identify. One of the drawbacks of sequential lobing is that multiple beams are needed. It would either need the same antenna to have multiple beams, which would complicate the system, and sometimes there is mutual coupling that cause issues. On the other hand, if we need two antennas to create the two beams, then also it can increase the aperture size and the weight. For the conical scanning, as the name suggests, here basically, instead of switching the two beams, the beams are rotated either clockwise or anti-clockwise. And this rotation or vortex of the beams basically locates the object. And whenever before the object is not in the beam's axis, as I say, the voltage will be lower, and then there is some sort of servo loop that will happen that would rotate this beam until the object is found. And that error, as it gets lower and lower, the direction is set more precisely. The problems of both conical and sequential lobing, as I mentioned earlier, that multiple beams are needed, and specifically more than 4 return beams are needed, which can increase the tracking time. To overcome those challenges, the monopulse systems are typically implemented. So there is amplitude comparison monopulse system and phase comparison monopulse system. Amplitude comparison monopulse system is the most popular approach. As you can see, what happens in monopulse is that there is, instead of switching two beams, there are two squint beams that are always on. And there is some sort of overlap, as you can see, and there is a common axis in the overlap area. So in this approach, there are two waveforms that are created. One is the sum, and the other one is the difference. So sum is basically the sum of this, and the difference is the difference between this. So the monopulse systems use the sum pattern on the transmit pulse, and the sum and difference patterns are used in the receive pattern pulse. The difference in amplitude obtained from these two beams, which is called the difference beams, gives us the angular error. And I'm going to show and talk about these equations. So basically this ratio of sum and difference voltages, if we take the real part of it, which is basically the magnitude of the sum and difference ratio, and then there is a cos delta function, and the delta is basically the error angle. And the phase difference between the sum pattern and the difference pattern basically is the angular error in the system. And as similar to the previous approach, there is a control system to move the beams in such a way that the angular error gets lower and lower. And in the amplitude compression monopulse system, if we plot the normalized delta sigma difference sum magnitude with respect to the pattern angle, there is a linear region where we can get a certain slope. And this slope is called the monopulse slope constant Ks. And theta b, which is basically the half power beam width, basically half power beam width is the beam width where the power level is 50% than the peak power. So that ratio is basically nothing but approximately Ks theta, where theta is less than or equal to theta b by 4, or 1/4 of half power beam width. So the phase comparison monopulse system, as opposed to amplitude comparison monopulse system, have two beams that are not like have a separation like you saw in the previous figure, but they are like at the same location. So their beam axes are aligned. And here basically the projection of the target on each beam and the amplitudes of the returns from the target received by each of these antennas are the same. And here basically the phase differences are utilized to track the moving object. So with those backgrounds, I'll just briefly talk about what we have been working on for beam steering and millimeter wave antenna array development. We are particularly in this talk, I'm just going to talk about some of the antennas that we have implemented and their performance. So the first antenna that we implemented as a single unit for the V2V communication is a Vivaldi antenna, which is an end-fire antenna, meaning it radiates along the board side direction. And we did some modifications in the design that to increase the radiation efficiency as well as the gain. For example, as you can see, there are some corrugations that we implemented to reduce the side lobe level and increase the gain, as well as the meta surface elements in the opening of the Vivaldis to increase the gain. So our goal was to achieve very compact size so that even if we create an n number of elements, let's say eight elements or 8 by 8 elements, the design will be still smaller in aperture. So our implemented system is only 25 millimeter by 13 millimeter. The realized measured gain is 11.4 dBi. It is linearly polarized, but we are working on implementing this in a circular fashion with a feeding network to achieve circular polarization. And the half power beam width is about 60 degrees for this single element. From the reflection coefficient graph, as you can see, the frequency range is from 26.8 gigahertz to 54 gigahertz. So it very much covers the Ka band and some part of V band. And the fractional bandwidth is about 67.3%. And we did measurement of this antenna in an anechoic chamber. And our measurement results showed a peak gain of 11.4 dBi and very much similar radiation pattern as the simulated result. Here you can see some more simulation and measurement results. So basically what we did some step-by-step simulation to see how the bandwidth is enhanced as well as the gain is enhanced for various modifications of the design. As you can see, the regular Vivaldi antennas have achieve a 9.21 dBi. As opposed to that, when we have the modified design, we have almost 3 dB increase in gain, which is 50% more radiated power in the desired direction. And as you can see, as the design evolution happened, we also see the broadening of the reflection coefficient bandwidth, as well as, the reflection coefficient gets lower, which means there will be lesser reflection. Radiation efficiency will be much higher. So all in all, our bandwidth specifications, which was more than 50% fractional bandwidth, was achieved. Greater than 10 dBi gain was achieved. It was compact and simple design. And now we're working on the beam steering scheme development for this array antenna. So we did some quick simulation to identify how the gain increases as we, for example, have a linear array and the n increases from 1 to, let's say, 8. Obviously, you might be asking why linear array. This is just for the demonstration. Linear might not be the feasible solutions because we would have to optimize the pattern based on the single elements pattern. But anyways, for linear array with lambda by 2 spacing, we did some simulation and we identified the various gain increases as the number of element increases. So for the 8 element, we see the gain is about 18.8 dBi. So with that, we utilize the Freeze equation, which we all know, basically the received power divided by the transmitted power is equal to the gain of the transmitter, gain of the receiver, wavelength square, and 4 pi d square, which is d is the distance between the transmitter and receiver antenna. So here we are assuming both transmitter and receiver antennas are same antenna with a gain of 18.8 or 18.2 dBi. And we try to identify what's the path loss in dB, because that's what we want to make sure, because there is a limit of transmitted power. We cannot transmit as much of power as we would like. There is limitations in terms of the power amplifier that's available or the system battery that we can provide in the UAV. And then there is also receiver sensitivity. We cannot go beyond that receive power, because if we go below the receive power, the receiver would not be able to detect it and there will be bit error rate. So with that, we can see as the distance increases, how the path loss increases. So from our initial calculation, we saw for 30-meter distance, which is basically the maximum link distance that we are targeting, the path loss is about 56.42 dB. And from the commercial beamforming ICs from Leaky-wave or analog devices, we can see this would be possible to be implemented without any problem. So now I'll switch the gear to a different type of antennas that we also are investigating, and that's called leaky-wave antenna. So leaky-wave antenna is nothing but some sort of waveguide based antenna, where there are openings or slots from where the radiation emits. And in this particular design, you can see the slot pattern is kind of like a W shape. And there are some resonators at the beginning of the waveguide that's implemented to make it resonate a certain frequency. And I'll not go through too much details about the design equations, but in terms of performance, what we achieved is we were able to cover the 57 to 62 gigahertz minus 10 dB bandwidth. And the maximum gain from the simulation results was about 13.43 dBi. And we were able to see the radiation efficiency to be much higher. Again, this is simulated and we have some measurement results as well, but in ideal case, it was greater than 90%. One drawback of leaky-wave antenna is that the beam steering typically happens when the frequency changes. For example, this antenna operates from 57 to 62 gigahertz. And as we change the frequency from 57 to 62 with certain increment 0.5 gigahertz, we can see the beam steers from 22 to 54 degree in the elevation plane. So the transmitter and receiver needs to know at what exact frequency this is being transmitted, and there's some sort of communication needs to happen to identify the frequency. We also built the prototype and did measurement in our lab. There were some issue in the transition, and that's what we modified it in our later version. But even with so, we saw that in the measurement, there are prominently two bands. One is around like 56 gigahertz or so, and the other one is around 66 gigahertz or so, that we saw less than minus 10 dB return loss. And the beam width identified was to be 12.1 degree, and the side lobe level was less than 12.7 dB. To compensate for the return loss or reduction in efficiency in the feeding network, we designed a ground coplanar waveguide transition. And with the transition, we saw a much better performance. Instead of the two bands, we were now covering the whole band from 57.9 to 61.5 gigahertz. And the radiation efficiency was also almost close to 90%. And then here you can see some of the results. Like, for example, maximum gain was increased to 13.5 dBi. The beam steering range was about 37 degree. Although you can see it is obvious in Leaky-wave antennas, the beam is a bit tilted. It's not in the board side like conventionally in patch antenna array that we see, but this can be compensated by placing this element in such a way that we cover the board side. We also implemented another version of SIW, or substrate integrated waveguide antenna, which is elliptically polarized. And this basically is a multi-layered design where at the top we have the bow tie patch, and the bottom we have the substrate integrated waveguide to drive to excite the antenna elements in the top area. And then the frequency performance showed a wide band from 48.5 to 62.3 gigahertz. And the axial ratio, which is about 7 dB, depicts it's elliptically polarized. And the radiation efficiency is more than 80%. We also did measurements of this prototype, and we saw the minus 10 dB bandwidth is pretty high, covering from 50 to 75 gigahertz. And the measured gain was 8.34 dBi, and radiation efficiency was greater than 86%. Here are some more simulation results showing the electric field distribution. And we also tried to create an array out of it. This is the array configuration where 4 elements are placed in this way to achieve unidirectional beam pattern. And here you can see the various measured and simulated S11 as well as efficiency graphs. So overall, this system achieved 9.5 dBi gain. It sort of achieved various bands within the V band and W bands as well. And efficiency is greater than 90% with a total bandwidth of 13.5 gigahertz. It achieves linear polarization in V band and circular polarization in W band. And the compact design is very attractive for making it implemented on UAVs. We did some sort of substrate analysis as well, Rogers versus FR4. And obviously Rogers being a very low loss dielectric, we can see the gain is much higher for Rogers as opposed to FR4 where the gain is very low. And the radiation efficiency also depicts that. So for future work, we have lots of things to do. One of the ideas that we are trying to implement is adjustable beam coverage area. Because as UAVs are going to move, sometimes they're going to be really close to the transmitter, sometimes they might be really far. So depending on that, we would need to have an adjustable beam coverage area, because if the UAV is really far and we have the beam width very narrow, like pencil beam, then it would require really highly intense, highly, complicated beam steering system that would need to steer the beam every second, which would cause, complexity. And when it's very close, then probably it makes sense to do, narrow beam. So depending on that sensing of the object, some sort of adjustable beam coverage is needed to be implemented. And then dual circularly polarized arrays are important because if it is not circularly polarized, then what happens there, it's not always possible to maintain the alignment between the transmitting and receiving antenna. And if there is some sort of misalignment, that causes the polarization loss factor to be much higher, which can increase the path loss. And why do we need dual circular polarized is because we can then use right-hand circular polarized waveform for tracking and left-hand circular polarized for communication link. And the next step is we are investigating on the best active beamforming systems to be integrated with the arrays of antennas to implement the beam steering and the control algorithms for that. And then we want to achieve more than 45-degree beam steering for each individual array. And then we will be placing the arrays in different locations to cover the front, back, top, left, top, bottom, left, and right. And dual circular polarization, as I mentioned earlier. Obviously, we also need to identify substrates that are lightweight, doesn't increase the payload much, but also with low dielectric loss to enhance the coverage and the gain. With that, I would like to acknowledge the IEEE Vehicular Technology Society for the sponsorship of the webinar series on advanced air mobility system. And I'm open for taking questions.
Yeah, so thank you, Ifana. That's a wonderful presentation, very timely and valuable. There is a chat. In fact, I will read those questions and you can answer, or if you feel comfortable, you can read the chat by yourself. So
you can read, I think, yeah, and then I can answer.
The very first question is that okay, any analysis comment on the side lobe level requirements in millimeter wave sub-terahertz bands? You already answered this question, but probably you may want to summarize.
Yes, so basically it depends on the system specifications, right? Typically for radar, specifically for millimeter wave band radar for defense applications, it might be required to be less than 20 dB or 25 dB. But again, it depends on the system, the active circuit and the requirements for those, right? But for us, I think we set this SLL to be 15 dB. 15 dB is a good starting point, I think, for communication type of systems.
Next question isn't there any standard which define the usable bandwidth in UAV?
I mean, I think you can answer this better than I do. So maybe you can comment. I think there are some standards, right? I mean, we were talking about various standards for base station to UAV and then UAV to UAV, right? The particular band that we looked into for base station to UAV was probably C band, right? That's it's a defined band that was there in the literature. But for UAVs, I don't know if there is any specific FCC band allocated. Do you know of?
Yeah, it is correct. Actually, they're still in works, just for between UAV to UAV, even for UAV communications, the specific band it varies, of course, in a different probably different countries. But in the US, the Federal Aviation Authority is still working on this. One consideration is this 5 gigahertz band, but nothing is defined yet. You're right. Okay, the other question is, as you said, feed network gets quite complex for large arrays. Any comments on leveraging space feeding instead of guided wave feeding?
Yes, so this is basically the future, right? I mean, there are some calls from DARPA that I saw recently that was for, you know, very futuristic. Like you would not need any physical interconnect between the elements, right? So you have some sort of, beamforming chip that has the generator, but if there are hundreds of elements, it very gets cumbersome, right? So is there any optical means to excite those elements or some sort of other means to excite those elements instead of physical interconnects or waveguide based? So
No,
that.
no, no. That was not the question. This is question from you, Berlin. So
Mhm,
typically, space feeding has been used since 1963 for reflector rays.
mhm,
And now there's quite a large amount of work from Antenna Society and also from Comms Society, where they take a very large reflector array
mhm,
and they use the space feeding. Space feeding meaning that we use only a small active antenna at the focal plane,
mhm,
and the energy is coupled from the feeder to the
mhm.
reflector array using the free space propagation. Any comments on that?
Yes, so yes, we have been working on reflector arrays as well. And one of my students, I didn't show the reflector array work here, but we did implement a millimeter wave, very wideband reflector array. And since this work has not been published yet, I didn't present it yet. But there's always challenge of, how to mount it on the UAVs because you need a feeding network, right? I mean, a feeding like, horn antenna, and that how to mount this on the UAV. There's RCS that we also need to consider, right? It can increase the RCS specifically for defense application, and moreover there is issues of blockage, right? Because it's in the main aperture, so we probably need some sort of off-axis feeding to reduce the blockage. So we are investigating on that. Unfortunately, I didn't include that here, but we are also working in that area. Does that
Okay.
answer your question?
Okay. Yeah, probably we can take it offline. Recently, there was a result that using the principal eigen mode,
Mm-hmm.
the feeder is very small and
Mm-hmm.
there is a natural taper in the feeder array or the feeder aperture and the reflector array aperture. And that leads to the side lobes of the order of minus 50 dB. That is very important because the phase shifters can then be digital and the hardware impairments also will not cause the side lobes to go higher than minus 35 dB. That is one thing. And when you say minus 15 dB side lobe, that means the range is quadratic in the distance. If 10 times is the side lobe suppression, and if I want to avoid any interference or jamming, that means my dynamic range is restricted to 3. So from that viewpoint also, probably these side lobes, ultra low side lobes of space feeding may be useful. That
Mm-hmm.
is what I was thinking. I thought I would
Right.
your comments on. And slide number 17, you had shown a table where you increase the number of arrays, antenna number of slide 17.
Mm-hmm.
Yes. So if we see the table at the center, bottom center, lower center, for a two element array, the gain is 13.4 dBi.
Mm-hmm.
And for a four element array, it is 15.3 dBi. Typically, when we go from 2 to 4, it should be 3 dB gain. And so the expectation would be 16.3 dBi. While this holds when we go for a larger number of elements, but I was wondering why specifically for the four element, the gain is not 3 dB.
Yeah, so this is basically not a physically implemented array. This is basically using the CST's array factor uh, calculation where we just mentioned the lambda by 2. And so this is by no means is an optimized array, as I mentioned in the beginning. This could be possible due to the mutual coupling between the elements. I mean, I did not plot the S1 here, or I didn't look into it. Um, the mutual coupling might reduce this gain
But
drastically.
that should also have been there when we go to the 8 element array. There we are getting the perfect scaling. Anyways, I understand that that was not the focus. And there are a lot of other questions which Kamesh will lead. But one very pressing question, because you are from hardware background, what is the typical monopulse constant Ks you have shown on your monopulse slide in view of millimeter wave hardware factors? Monopulse slide.
Yeah.
Next slide. Yeah, what is the typical value of Ks from hardware experience and expertise, which which should be your basic core contribution?
I did not implement the monopulse horn antennas yet, so I don't
Okay.
remember on top of my head what is the typical for millimeter wave, but I can look into literature and then give you that answer. I'm
Fine,
sorry.
thanks. Then thanks. Sorry,
Yeah.
Kamesh. The question was not clear, so I had to interrupt. Now you can carry on.
You did a good job, and please follow up offline. And first of all, thanks for the interest in this presentation. Then probably we have one more last thing. I think Krishna Kumar, it's mostly your question, so why don't we take these offline?
Yes, please do contact me over in emails. My email address, I think, Kamesh, or I can put it on chat and we can talk offline. Yeah.
So Ifana, it would be great if you can just give your comments on these points, and then from there we'll take it up, because I've already put the questions in the chat window.
Sure,
Yes,
sure.
I've not
I'll
put
take a look at it. Yes.
Thanks, Ifana.
Yeah.
In fact, just a comment from John Fregal is that new AV systems are planned to carry passengers remote piloted. So I think there's not a question, but I believe he's suggesting that we have this. This is real, and that is true, John. This is coming to real world. Air taxis, air ambulances are coming to real world. In fact, both Professor Ifana Mahbub and many professors in this area, DFW area, are witnessing this evolution right in front of our eyes. So it is an exciting time. In fact, we are almost time. I will just want to mention one thing very special about this today's presentation. Professor Mahbub is a mother. She is handling both family and as well as research at the same time. And Katie, the organizer who has been helping us with Advanced Air Mobility webinar, she's also a new mother. So this is very special presentation in the Advanced Air Mobility series. So and a salute to all moms in the world.
Thank you.
All right. So with that, we are wrapping up this presentation, and please join us. Please continue joining and attending these events. And all these presentations, from the very first presentation to until now, all these presentations are recorded. They are available. Include the slides are also made available separately. Thank you to VTS and especially to Katie and her team for organizing this wonderful series. Thank you very much, and have a wonderful week and wonderful day ahead. Thank you.
Thank you. Bye.